Welcome back. Today we're going to try to get a little bit more into the meat, into the operational of it. Let me remind you from yesterday. You have some problems to turn in. This is not to come and see someone else do it for you. You're turning it in and then getting it graded. It's not a lot of points. It's not about the grade, but hello.
Is this on already? Because I didn't find your lecture.
There should be PowerPoint and also a PDF of the lecture notes. Did you check by any chance?
No, I just looked with you ordered it already.
Yeah.
Like I said,
But you looked at it, you didn't see it?
I didn't see it either. Oh, I can check, right?
And do you mind writing to me? And
Yeah.
okay, thank you for asking. Okay, and then I just want to remind you what we were doing yesterday. We were looking at the phenomenon that as you rotate the molecule, you get a different readout frequency, and we were casting it as a 3x3 tensor, and we were drawing attention to the fact that we know that our observable, for just measuring shifts, for just that one thing, is only one element in this tensor. Now that tensor is naturally written in a principal axis system, and we're starting to learn to rotate it into the laboratory frame. Now, everything we're doing is also going to be useful for a dipole coupling between two spins, a physical picture where one spin has fields and the other one is a spectator to those fields. And so where are you in space is a big deal. Could be raising your frequency, lowering it, whatever. The same apparatus we're developing for CFA is going to be helpful for that. Many of the expressions that we've been exposed to are simplifications. We're not going to start with a simplification here. What we're going to do is our cursor back, first of all. Here we go. We're going to go to the blackboard for just a second. Doing that. Good. All right, so you know, dipole, you've heard of a dipole, and we have a classical expression that we're going to rewrite with the correspondence principle. So it's a 3-factor u0 over 4 pi r cubed. And then that classical expression was the dot product of the two dipoles, which you would have thought you had to stop there, but then there's this other funny term. -3. And you take the first dipole and you dot it in to the internuclear vector. Then you take that internuclear vector and you dot it into U2. And if you look back at your undergraduate this class, you'll realize that you recalled that a long time ago. It's an expression that comes from Taylor expansion, monopole, dipole, multipole. And it turns out for nuclei, as for their magnetic properties, they don't ever have a monopole because apparently nobody gets to have a monopole. They also don't have a quadrupole. That's not what a quadrupolar nucleus is. They don't have a magnetic quadrupole. And people have checked all the way up to how do you pronounce it, hexas, up to 16, we don't have them, okay? So it's just a dipole. That's all it is for magnetic interactions to the accuracy that we need. And so we can take this classical expression and we can use correspondence to turn it into, instead, u0 over 4 pi r cubed. And then this will be a quantum mechanics expression that looks just the same. I'll have the two terms. So it's I, which is a vector because it's a vector of operators, operator ix, I, y, and id, dotted into s, another vector. And then we subtract 3 times. And then it's going to be this vector dot r, and then r dot into s. So it's the same thing, it's just written as quantum mechanical operators. Now, in a second, we're going to look at something where we can rewrite this, and it's absolutely equivalent to say, if I have I dot r and then r dot s, I can say I dot r outer product r. I can regroup them like this. We're going to look at this property in a minute. But for the moment, you just have to have a leap of faith, that I'm allowed to reconstitute it like that. So we're gonna look at an outer product. And for this dipole operator, may I just show you the result that I got as the pass-through, so I can put a 3x3 second rank tensor that looks like the identity operator, and that's still I dot S. It takes the X of I and the X of S and marries them on Y and Y, Z and Z. So it may look like just elaborating something instead of simplifying it, but I'm allowed to insert a unit tensor there. Our outer product with R means in the first element, I take the X piece of this R, and then that's for the row, for the first index, and then for the second index for the column, I take the first index of this one. So this would be the third index, the third component of the first index, the third component of the second index. So over here, for example, I would take the row, so second component for the first index and the first component for the second index. So I would go around and fill this in, the outer product works that way, that out of two 1x3s, I get a 3x3. And if I go into the principal axis system, our outer product with R, I can say is the same as Z by Z. I choose that R along Z, means I only get this one entry here in this free element. So therefore, we can write a matrix in the principal axis system that represents both of these terms, this unit tensor and this R outer product with R, but it has a factor of 3 in front of it, in this way. This is our spatial degrees of freedom tensor to represent the dipole. It has a size, which I can pull out front. It relates the two spin operators to each other. And this is the tensor that describes how the molecule is formed. This is the tensor representing these two copies of R. Okay, so all the time these rank 2 tensors represent, in a way, two different vectors that have been combined in this special Alice product. So the dipole coupling, like the CSA, can be addressed with exactly the same mathematics that we've been talking about here. Just so that you understand that, we're doing a lot of work to set this up, but you can use it for any of our tensors, and we know how the dipole in particular looks, and we're interested in the dipole. So the way that we're going to do this frame transformation, we want to rotate tensors, like that dipole tensor, or like that arbitrary 3x3 CSA tensor. We want to learn how to rotate them for the purpose of doing a frame transformation. And we had just gotten to the point of saying the smart way is not Cartesian. The smart way, am I in the right spot? Yeah. The smart way is not Cartesian. The smart way is to decompose your matrix, whatever it is, whether it's simple like the dipolar or kind of cluttered like CSA. You're going to decompose it into angular momentum components, and those are what you're going to rotate. And it sounds like how, complicating things, you'll see that it's an elegant simplification for it. So you could take the overlap of the inner product of whatever tensor that you want, whatever vector you want, take it with a basis vector that represents angular momentum component, like L equals 1, M sub L equals 0, whatever you want. Project that out, that's the component for that kind of angular momentum, and then we'll have a rule for rotating that. And the rules will be so much simpler than those big R matrices. So in here I say a classic example of a second rank tensor is the outer product of the vector of itself. We'll just start with that for the dipole color. Symmetric about the diagonal. To rotate it, you will need to rotate two copies of R. So do you remember yesterday that we learned that our CSA tensor has to be bilinear or rotated twice, or operated on R from before and after. This kind of helps you see that, right? If you can make a 3x3 tensor representing this physics out of combining two R's, it seems like any other answer would be wrong. I have to rotate each of those R's. Okay, so our tensors are rotated as a sandwich. But if you took out of your matrix and L equals one object, that thing should only be rotated once. If you took out of your tensor and L equals 0 object, rotate it. Doesn't need it. Okay, so you're going to rotate each thing that you pull out of that 3x3 appropriately, according to its angular momentum characteristics. Now here's our arbitrary matrix. This is where we left you yesterday. Any 9 numbers, whatever. From that, I'm saying, let's do a spherical harmonic decomposition. And it's going to be a column vector. The way I like to think about it is like a 1/9 column vector, where there's a chunk that's the L equals 0, another chunk that's the L equals 1, and finally a bigger chunk that's L equals 2. And what are the values for these components? Well, it's this combination of the original 9 numbers, because those represent the projection of these bases. Matrices that are the kind of crystalline, that's your angular momentum. This is an angular momentum of 0. These are some angular momentum 1 objects, and these are some angular momentum. So you're basically projecting that on M, and you're going to get this coefficient, so that's what you put in that entry. So we're just rewriting the matrix. Instead of one matrix, we now have 9 matrices, but they're all beautiful, well-behaved objects. So you could, this is not something to turn in. You could, and I think if you're going to study this stuff more in your future, this is probably the best exercise I'm assigning you could confirm that that spherical harmonic basis set, those matrices with 1s and i's and things like that, are orthonormal. They span the space. They are eigenoperators of RZ, whereas the Cartesian pieces never were. They never had those beautiful forms. Okay, you could confirm that, and I'll do a trivial case for you that is so stupid that you're going to not say thank you, but it shows you the mechanics how you would go about that. M00 is this matrix. So I take that matrix and I rotate it around Z through an angle phi. If it's an eigen operator of RZ, shouldn't matter what phi is, I need to get the same thing back, 4 times constant. So I do that rotation and I get the same thing back. And you say, yeah, that's like L equals 0. Anyway, I get the same thing back. But that's how you would go about it. I've just shown that that's an eigen operator of RZ. That matrix.
On the right hand side, are we missing the other R or like the double operator symbol represents?
This is R inverse R.
So on the top and on the equation.
Oh, that's because, yeah, that's a super operator. Yeah. Operator who acts on an operator. Okay, so does that make sense as an assignment? So I'm claiming, hey, use this basis set. This is a really cool basis set. Question that should occur to you, even if I didn't say it, is it complete? Is it orthogonal? Is it normalized? And what did you say last time? Eigenoperator or what? So you should confirm all those properties, okay? Or not, you could just trust me, but telling you I do make mistakes, so confirming me is a good idea. Now, we're using this to do this transformation. We, generally speaking, need to go from the PAS to the lab, usually by way of some other frames, so we have this problem of a nested transformation. So let's get on to how to rotate these things. I said here's the basis of that, decompose it, you'll enjoy it, but like, I still didn't say how to rotate. Now, before I say how to rotate, I got one more thing for you. This is in the lab frame. This is in the lab frame. This is naturally in the PAS. This is spin degrees of freedom, spin degrees of freedom. It's about the magnet and the spin. This is on a molecule, something written on the molecule, a truth about a molecule. So I could say these are spatial degrees of freedom, meaning when I move the molecule around in space, they change. And these are spin degrees of freedom, both of them. I feel like it's a little awkward that the spin is showing up here and here, and like, I want to group them, so spin is here, spin is here. And the reason I'm really doing that is that out of these two vectors, I'm going to make one tensor. So now the spin and the spatial are very analogous. They have the same rank, they're the same kind of object. Okay? And we can treat them the same. So not only is what I'm about to show you good for the dipole as it is for the CSA, it's actually a good thing to do to your spin. So how am I doing that? How am I combining these two vectors that are way on the outside and putting them together into one object? Or a kind of more compact way to write the Hamiltonian. I'll show you in just a second. But let me also make sure we're okay with the nomenclature here. So both, spatial and spin are going to have angular momentum indices. So it's a 3 by 3, but it's been decomposed into its basis set. So this is the sum over L and over M. So there are 9 of these RLMs to add up. And as this, then you're going to be using the same basis set for the R and the T, for the spin and the spatial. You only match like components. So if in the spatial I have L equals 1, I am not going to waste my time multiplying that with the spin with L equals 0. It's orthonormal basis that I don't have to multiply. I know in advance it's not going to be. So there aren't 9 times 9 of these. There are just 9 of them. You just project the same symmetry height. Okay. So this is a sum of 9 objects that look like this, but you're changing out L and M until you're done with this. Does that all make sense? So both the spin and the spatial terms can be thought of as a second rank tensor. And the way I'm doing it is I'm taking sigma, I'll leave it the way it is, it already was. But I'm going to take B and I, and I'm going to do the same thing I showed you over here on the chalkboard. Outer product, B and I, you start out with 2 1 by 3s or 3 by 1s, and you combine them and you get a single 3 by 3, a larger object with 2 indices, because you have 2 indices, you have 2 like degrees of freedom or indices, this one and this one. So in the second rank, you have 2 indices. Now, you're collecting all the spin degrees of freedom into one place, so you can think about how to rotate that thing. And as I mentioned in passing here, but now it's formally in the notes, the ij element of outer product of B and I is you take the I element of B and you multiply it by the j element of I. And so that's just a systematic way to build the whole thing. Okay. Outer product of 2 vectors with entries ui, vi is a tensor, with entries mij equals ui. And it's an m by n matrix. Now, this fits into a list of ways we can combine tensors. We can take a dot product, we can take an outer product, we can take a regular matrix multiplication. And we have to do all of this. And so, you always have to stop and look at the operation to say, which one are we talking about? Is that reducing the rank, preserving the rank, expanding the rank? And I just put a list here in the notes of different kinds of math tools that get used in the class in passing. And each of you can think to yourself, do I remember that? Do I even know what that is? The only one here that I'm expecting is unfamiliar to you, that you may never have had it in any other class, is the one on the bottom. I'll talk about that on Tuesday. The rest of these, I'm really hoping this is a review, that you saw it someplace before, but I'm very sympathetic to the fact that it might be rusty. So you could talk with any of us, Anish or Art or myself, if there's some topic in there, you say, whoa, how is that supposed to know about that? So this outer product, B and I, is useful because it really gives you a nice way to write about the Hamiltonian, where sort of the spin and the spatial are on equal terms. And it's not just that we're learning one tool for both of them, it's that the fact that they're in the same basis, that means that we eliminate many arithmetic operations by inspection. I'd like you to confirm something important here. I said that B dotted into sigma, which is then dotted into I, is the same as the outer product of B and I dotted onto sigma. I rearranged it and I just said that's the same. But you can confirm that. So you just write them out explicitly and do the operation and see if you get the same thing. Does that make sense as an exercise? So I have a solution, but I'm not going to show it to you. Okay. This allows us to use orthogonality. I said that already. Often spin degrees of freedom such as B cross I are expressed with spherical harmonics and spatial degrees of freedom as well. And then those two get multiplied, the spin times the spatial. You only have 9 operations like that. In other words, the L equals 2 M equals 1 component of T only gets combined with L equals 2 M equals 1 of R. So I'm using T's and R's to this is the Spice nomenclature, probably comes up soon. But for spin and spatial, respectively, those are the symbols that Spice started using, so a lot of us use. When calculating the inner product of tensors, spherical harmonic notation, only project the corresponding elements, same M, same L, but also only compute what you need as an observable. So what we knew is that it's the free element. What is that in spherical harmonic? And only do that, don't do anything else. Okay, that's very, very few operations. When you apply both of those rules, you have so few things to move. Now, we're putting it together in this format that I showed you already. There's a scaling factor on the front that'll have your units, get you to energy units. You have spin and spatial characteristics in there. And all of that together gives you the energy divided by, it should be H, not H bar, which is omega. And for the CSA, I have a table I prepared. It's partly based on Spice's wonderful book, and then a couple of little corrections here and there, where I show what is C, what is that number out in the front that gives you the right value in units. C in this case is minus gamma. And then what is the spin degrees of freedom, which are T, what is the 0, 0, what is the 1, 0, what is the 1 minus 1? So what are these things as being combinations of the computing things that we've been using all. So T00 is an isotropic shift, and it's I0, B0. T1 plus and minus 1 is a raising or lowering operator applied to B9. T20 has no Z component of the angular momentum, but it does have angular momentum, and it also takes the character I0, B0, which is interesting. T2 plus or minus 1 is again a raising and lowering operator. And actually, for this particular interaction, T2 plus or minus 2 is 0. So we can ask the same question over in the spatial degrees of freedom. What is R00? If we took the CSA, written as a matrix, and reject out 0, 0, what is it? It's the isotropic. The average of the diagonal. R, L, comma, M. I left it off. It's a big expression, but we don't need it for anything we're going to calculate until we come back to relaxation. R20. That's where delta shows up, and it has a scaling factor. So if you wrote your CSA in a principal axis system in terms of delta, you would find that R20 is delta. So it's like the difference between the ZZ element and the 1, 1, and 2. 2 plus or minus 1 is strictly 0, and R2 plus or minus 2 is like eta. It scales with eta. So when you decompose your Hamiltonian into the spherical harmonic components, and you can do that by hand, you're getting 9 of these. I gave you the rules on another slide, how to pull those out, and now here I'm giving you what I believe the right answers are. These are all things you can also do. You understand what the definitions are, you should be able to reconfirm that this slide is correct. And here's a table of answers for the dipole. So these will help you work problems. Now, we like this. We can eliminate many pieces that will be 0 in the final answer. We can avoid calculating things that are not observable, and we don't bother rotating things that don't need to be rotated. And so let's go right to it. So any matrix, it could be T, it could be R, or it could be any other matrix. And this is for a rank 2 that I'm thinking about here. So we'd have to make a little tweak if it wasn't rank 2. But anyway, if we want to see it in the lab frame, but we only know it in the PAS, the first thing we're going to do is recognize that this is the sum over L. So for each component in the PAS frame, we have to do a calculation. And then we're going to add all those up. Now, if we're talking about L equals 2, this is going to be a sum of 5 pieces. Now, you add a PAS component for that M prime, which is a dummy variable that you're summing over. It does not appear in what you're going to get in the lab frame. Right? So let's say I'm trying to capture M equals 0 in the lab. Typical case. I want 2, 0, L 2, 0 in the lab frame. What I'm going to be doing is saying, well, remember that an L equals 2 object can rotate and become a different component of an L equals 2 object. I cannot rotate an L equals 0 or 1 and make it into an L equals 2. But it could have come, I want L equals 2 in the lab frame, L equals 2, M equals 0. But that could have started out of the PAS as any of the 5 L equals 2 components. So I'm going to have to start with every single one of them separate. So I start with M equals plus 2, and I do a calculation of how much of that will end up lining up with the M equals 0. And then I come to the plus 1, and then I come to the 0, the minus 1, and the minus 2. So I have to ask for each of the components in the principal axis system after the rotation, how much of it lines up with the component of interest in the lab frame. And this is somehow a projection that represents the linear recombinations that happen on rotation. Now that projection is a function of 3 angles, because that's how we do the rotation in 3 angles. When we rotate around Z, you get the same thing back with just a phase factor. So the operation Z is real simple. It looks like e to the I m, whichever component you're calculating at that moment, and in the alpha. It's the angle that you rotate through. Phase factor. That was by construction, because we made these things be eigenoperators to Z. And this is a linear component. This is like a projection. So of the rotations around Y, you're literally projecting different M values on each other, and let's look at what those functions are. It's just a linear remix of the M components. So rotation is a linear unitary transformation. It preserves the norm. It's represented by D in this case, not R. The various values for L are not interconverted. L equals 0 doesn't have to be rotated. Rotation by Z returns the same tensor times with a complex number. The job of our Y in green here is to remix the elements of the same L and different M. And how much of each do you get is a function of the angle. So here's a cartoon to go with all those words. I do not remix these. I do not start with this and end up with this. I do not start with this and end up with it. But I do start with one of these and end up with a mix of it, as I just changed my point of view. I don't turn this into any of those, but I do turn it into the others, just by changing my point of view. However, if I rotate from one frame, the PAS, to the laboratory, there's some interesting things to keep in mind. If it's a symmetric molecule, I only have to start with one of these components. So I don't have to do 5 times 5 calculations. I don't have to do all components. I could say in the PAS I only have this one, but if it's a single molecule. Also, when I come to measure, I may only measure this. So sometimes I only have to do one calculation for the entire tensor, one calculation. I just have to be smart and realize what I need and what I don't need. So let's look at L equals 1 for a minute. Even though it's not an NMR observable, it's just easier. It's a vector-like thing, and so we know how it behaves. If I say L equals 1, and I need to rotate those components, so I want to know in the lab frame, for example, I'm interested in how much L equals 1, M equals 1 I'm going to end up with. The thing I need to do is say, well, in the PAS, how much did you have? Whatever that is, multiplied by J. Well, what's J? It's trigonometry. Depends on base. Of course, it depends on where angle we rotate. Yeah, but that isn't the only thing I'll have, because what happened to the stuff that started out as 0 in the PAS? Well, yeah, that might be in there too, but you have to multiply it by K. Right? And then what about the stuff that was originally in the PAS was -1? It needs to be multiplied by L, which often looks a lot like J. All right, then you add those 3 things up and you will answer the question, how much do I have in the lab frame of that one spherical harmonic? So that is this calculation. That's the figure rotation. So if I know alpha, beta, gamma, I have to just write down these 2 base vectors, go look in the table for what D, L, M prime N is. It's a piece of trigonometry, go find it, fill it out for your angle. That is the projection of one spherical harmonic component on the other during a rotation. Starts out at L equals 0, or L equals 1, M equals 0, ends up as L equals 1, M equals 1. Does that make sense? Each of those is a projection vector. They're a projection vector. Okay. Let's do an example. Rotate Z, around Y. And I'm going to do a dumb one, then you have to do one that makes some sense through an angle of 0. Okay? So I represent the Z vector. I have to decide what a Z vector looks like in spherical harmonics. And I'm claiming something here that we could discuss debate later, but it is L equals 1 for sure. But what M sub L components is Z. Z you have to add the 1 and the minus. And then to make it normalized, you have to divide by square root. So I could also write it as being this kind of an L equals 1 vector. It has this amplitude on 1, 0, minus 1. So it has that much of the L equals 1 and M equals 1, and that much of the L equals 1 and M minus 1, and no L equals 1 and M equals 0. So that's my representation of a Z vector. Now, if I need to rotate that thing, here it is, the way it starts out, and I'm going to rotate it with this angle sandwich. And so what's gamma if I rotate it around Y? I don't need that. What's beta that's where my zero is gonna go. I'm rotating around y by zero. And again, I don't need this, because I don't need an alpha, I just need beta, it's a rotation around y. So what I'm gonna do is fill in for beta equals 0. So if I fill in beta equals 0 into this table, I get this. That if I have 1, I get 1 back and nothing else. If I have 0, I get 0 back and nothing else. If I have -1, I get that's correct. Now, if I put a different value of beta, which you're going to do, then you would find that you're mixing. So put in 90 degrees, put in 180 degrees, you will be seeing what happens to the z vector as you actually rotate around y by an actual angle. So it's this that's going to change, right? The values of the mixed components. Do you guys feel like you could do one for 90 degrees? Try. Try for the next 2 minutes, try. I prepared an answer for you to look at as a reward. I used to have one, but I got rid of it. We'll have to do it together. So we're going to prepare this table here. But we're going to use beta equals 90 degrees. What happens? What's J, for example? 1/2, right? We're gonna have a 3 by 3. Here we have 1/2. Now, are there more J's in the table? Yeah, we've already got 2 of the answers to take. Now, what is L? Let's do the other corners. What's L?
Remind me.
1/2. 1 plus and 1 minus, they can't be the same. 1 plus 90 degrees, yes, they can be the same. 1/2, 1/2, 1/2. All right, now what do we got to do? We got to do an N in the middle. What's N? Because we're doing 90 degrees. All right, and we're almost done. We got K's all around, except they have to have a minus sign someplace. What is K? 1/√2, and I put a negative sign there. Okay, so we know how to fill this in. Those of you on the Zoom, you should be writing it for yourself. You've got this filled in, this little table of projection factors or reduced Wigner elements, Wigner elements. All right, so what does that do for your answer? How does that help you fill in your answer? In this place, in your resultant, you need to add, so you're asking, what is M? What is M? 1, and I need to add up these 3 components. K doesn't matter, but J and L do, because there was no 0 at the beginning. J and L both multiplied by 1/2 and 1/2. So I would take the original vector, which is this times 1/2, and add it to this times 1/2. Looks like I'm going to get 0 for that element. So if I rotate around 90 degrees, I started out with this being Z, and after I rotate at 90 degrees, that's all. This element is completely gone. Do you see that? I'm multiplying these 3 numbers onto these 3 numbers, and I'm getting nothing. So there is no M equals 1 component after rotating by 90 degrees. Just take a minute and see what your question might be about that. have the M prime equals minus L to L. And then what else? We're summing over M equals minus L to L. And since we don't need the phase factors for this problem, we're just going to sum this with the phase factors of B1. We're summing B M prime M. These are all L equals 2. Okay. And this, what we're going to get is our component M sub. Right now we're calculating, I'm sorry, L equals 1. What do we know? M1, 1, we're calculating the M11 element. Okay.
Sorry, could you like get the camera to look at the board?
Yeah, we're using both for just a second, but I'll do that. So we're walking through this equation on the top of this slide, MLM, BLM, and the camera, getting my cursor back. So up at the top here on the board, we're calculating the 1,1 element in the lab frame. So we have to take the 1 M prime element, and what we want is 1 in the end. So we can fill that in. We're calculating just this 1 element. So we got to go through all 3 values of M prime and add them up. And so in each case, we need to know what our original vector had for an amplitude of that component, and then what these bigger projectors had. So in the original frame, these are the components. So when we have M prime equals 1, we'll use this one. When we have M prime equals 0, we'll use 0. When we use M prime minus 1, we'll have minus 1 over root 2. And then we calculated these things, and we're in this row here. So turns out for the M equals 1 component, the answer is 0. Like these 2 terms will exactly cancel each other. These 2 terms projected on these 2 elements will exactly cancel. So you got nothing as being the lab frame. M equals 1, M equals 1, and L equals 1. Can we just expand this out so you can see that? This is equal to, what is M11, the M11 term? It's this. This is our M11 term. So I just write that number, 1 over root 2. And what is D11? Is a half. You solved it for me, times a half. Now we come to letting M prime be 0. That's 0 because there was never anything there. So that's 0 here. And then the third one is start with minus 1 over root 2. And then we figured out that we need to multiply that by a half. So it's minus 1 over 2 root 2. So that is our 1,1 element. And you now can go through, so M in the lab, the first entry is 0. And then you have 2 question marks here that you could work through by the same procedure. I'm starting to see some nodding. Okay. So it's a series of trivial operations. questions about that before we go back? And those operations do correspond to this kind of a picture that everything you want to know about in the lab, if I want to know this one, in principle, I should start with all 5 of these and figure out what that D, that central element for the Y rotation in the big nerve, that mixing coefficient is. And then I need to start from all 5 and see what I get for the observable in the lab frame. So in each case, I need to know how much I started with, and then I need to know what D is, and I just add those up. I did an example for L equals 1 because it's easier. Now you can do the same thing for L equals 2 if you want. But the matrix has got 25 entries and about 9 different actual calculations within that. 9. So those are the coefficients for each of the values of M on each other as you rotate. This table is used a lot. You will get used to this table. We don't use the one that we were just playing with that much. This one is used a lot. Now, again, do you have to actually calculate 25 things? No, because usually in the PAS, you simplify yourself down to 1 or 2. And always in the lab frame, you simplify yourself down to 1. So we don't do all the calculations. I just picked one at random, and we don't need that one. We just need a couple of these. So here's the problem. Rotate 2, 2 by 0 degrees, 90 degrees, 180 degrees around Y. So for 0 degrees, you can fill out all these things and you can see that it looks an awful lot like an identity operator. Like whatever you put in, you get the same thing out. Right? You don't actually mix. But now you can fill this out for different angles and start to do a problem. Are you good with that? It's just like the L equals 1 that we just did. Just takes a little while to get used to the idea. Now, some of the problems I'm really stressing and saying you really should do this, and some I'm saying, yeah, just if you want to. This is a, yeah, just if you want to. There is a systematic way that you could obtain or derive these figure elements. Like if somebody didn't give it to you, or if you feel like there's a typo, you can by yourself figure out what they are. And the hint that I give you is that start out with a tensor, an arbitrary tensor, rotate it with arbitrary angles, so you'll see beta, you won't see actual values, right? And then project it on to the tensor. And then project it onto the destination tensor, and that will be your projection vector. You will derive a bigger element. So if you want to do that, it's there to do, but you don't need to. So let's remind ourselves how we simplify the lab frame. We're going to want Z. It only depends on the Z element can be detected, and so we've only been using the ZZ or 3-3 element. What's that simplification for spherical harmonic? It's the L equals 2, M equals 0 in the lab frame. But if that's the case for the spin degrees of freedom, that's also the case for the station. Only need the 2, 0 component. So we don't have to calculate all the other things. How about in the PAS? Well, it has to have L equals 2, or it will never end up in the lab frame as being the 2, 0. That's one thing. Obviously, only the L equals 2. And if it's uniaxial, you only need the L equals 2. Let's go back there. Do we have already a picture of that? In the PAS, we also may only need the L equals 2, M equals 0. So for many problems, there's only one calculation. That's why people love their uniaxial approximation so much. So that takes us to a certain place that we can start to calculate frequencies. We can calculate a frequency using Cartesian sensors. And we can calculate a frequency, the same exact problem using spherical harmonics, and we can see which one is more tedious. Right now, the spherical harmonics got everybody with their eyes glazed over, but we're going to see a difference in the calculation and the number of operations you have to do. And we can look at that a little bit today. We can look at it a little bit on Tuesday. And then I want to just mention where we will be going after that. The frequency that we're going to want most of all in the next segment is the frequency during magic angle spin. So we're going to set up 2 to 3 frame transformations that represent selecting a crystal, having it rotate around the magic angle, and then reading it out of the laboratory. So we're going to use these angles for that problem starting next Tuesday. That'll be our job on Tuesday. But right now, we're just going to do much more simple frequency calculation of just like it's a static object, like just a crystal that you place in the field, no MAS, whatever. And we're going to calculate the frequency, but we're going to do it using Cartesian, and then do the exact same problem using spherical, and see if we get the same answer, see what the operations they like to do. Now, you guys know that in reality, these calculations will probably be done by a computer for you. Like, like to write your paper on your biophysics, you're not going to be doing a lot of these calculations by hand. But this is just a stage that will make you better at troubleshooting programs or anticipating or having intuition about these calculations, right? So we just do a few of them, and then we'll move on to another topic. So you ready to practice some more rotation problems? Do you want a 2-minute break? I think Anisha's ready to lead you through some, right?
Yeah.
Is it a good segue for you to start, or would you like me to do one?
Okay. Before you do a problem again, can I ask?
Yeah.
Back on the slide that you had that whole formula it's working with again.
Yeah, sure.
Maybe you could walk through it, the number picture.
Absolutely. I think this is the best one, right?
Yeah.
Okay.
So M prime is the one that it's a placeholder variable for the frame that you're starting on.
Like PAS, right?
Yeah.
This is the same tensor viewed in a laboratory frame. Tensor didn't change, just your point of view. It could be any tensor, spin, spatial, CFA, dipole, whatever. But it has, lambda represents what interaction you're talking about. But it's been broken down into spherical harmonic components. So we're talking now about a component with a certain L value and a certain N value that we're curious about in a laboratory frame, and most of the time would be L2 and 0 that we. Now, it could come from some other component in the PAS. And this is an equation that tells you how much of that component projects onto the left. N equals 0, L equals 2. So what could ever end up as being 2, 0? Well, it could be 2 minus 2, 2 minus 1, 2, 0, 2, 1, 2, 2. So I got to have a dummy variable M prime, which represents all the different things I could have started with in the PAS that might have ever projected to that thing in the laboratory. And I just add, it's just linear. Okay. So it's a dummy variable, M prime is a dummy variable that we're going to add over. It's the components in the PAs. Now, for each of those components, they have an original magnitude. Maybe they were 0, maybe they were big, we don't know. And then this is something I scale them up, like how much of that persists after the rotation and contributes to that particular value. So in order to fill all this in, you got to tell me what both the original component you were talking about and what the predictable one that you want out in the lab. So that's why it's a matrix of answers. Now I have left out these phase factors just so we can focus on the Y rotation, the hard part of this. I'll back and talk about the phase factors later, but so this is like the Y rotation, which really projects one of the components at L equals 2 onto another, right? And how big is it? Well, it's an explicit trigonometric function of beta. And also depends on which component you were starting with and what you end on, right? So for L equals 1, there are 9 different options of trigonometric functions that you'll have to fill in. But we don't always need all of them. We don't always need all of them, so we'll find problems and we can just pull 1 or 2 of these to get our answer. And did that help?
Yeah, and so when you're saying, like if you were rotating around X, the only difference would be the J, K, L, N.
Would be different, but we don't do X rotations, we only do Z and Y, because this is not convention. Yeah, and that would be a slightly obnoxious homework problem to make you construct X rotation, right? Yeah, so you can make every rotation out of 2 Z's and a Y, which is weird. Other questions just about the nomenclature?
Can you also remind how we got the initial values?
For the vector?
Yeah, so we have.
Oh, I just gave them to you. So the one we rotated, and let's go to that slide, I said, let's represent a Z vector as 1/√2, 0 minus 1/√2. I just said that's what I think is the best way to draw it, and I didn't explain that. But it does behave like a Z. If you do this problem, you see it's going to behave just like a Z. So if it acts like a Z, it's a Z.
So for rotations of different angles that we are doing right now, let's say even for 180 degree, we use the same.
Beginning. Yeah, so it starts at Z, where does it end up after a rotation of 180? Okay? Other questions before we do one more problem? Okay, here's the case in the Cartesian coordinates. So jump back to Cartesian just for a minute here. What we need to do to calculate the frequency is to calculate R. I apologize, that should be R and R inverse. R inverse sigma off. And that back in Cartesian, if you remember from a week ago, we worked through the matrix for Euler angles, alpha, beta, and gamma, and we got this. But we're going to let alpha and gamma be 0 because it's just a Y rotation, and so that turns out to be a rotation around Y through an angle beta. Okay. So here's our CSA in the principal axis system. Just the symmetrized portion, the diagonal symmetrized portion. So our job, if we wanted to calculate this frequency in a Cartesian system, would be to take the inverse of that, times that, times that. And multiply 3 by 3 matrices. And it's, tedious and it's entirely doable. And you can take that home as an exercise because it actually is one of these 9 problems and see what you get as an answer. Okay, you just do that multiplication. And what do we need to pull out of the resultant matrix to predict the frequency? Do we return to Anish? If you're turning in Anish, you give them the whole 3 by 3, or what do you give? The element after the rotation. That's your frequency. All right, now if we wanted to do the same problem, but we say, oh, she keeps saying, yammering on about these circle hormones, let's do it that way. We have a Hamiltonian here that spin degrees of freedom tell us we only need the 2, 0 component for the spatial degrees of freedom. So we're going to rotate the spatial degrees of freedom, and we're just going to pull the 2, 0 out. L equals 2, M equals 0 element. That's like we just pulled the 3, 3 element, right? But here we get to just know that in advance and just skip some calculations. So we're going to rotate the spatial degrees of freedom using these operations and just calculate the lab frame to 0 element. So we have to remind ourselves of this table I gave you. In in degrees of freedom, in the truncated form, that's all you need. T20 is this stuff. In the lab, in the PAS frame, for the spatial degrees of freedom, this is all you need if it's uniaxial. We're gonna do uniaxial. I was complaining about uniaxial and now I'm using it. Guilty as charged. Okay, so when we start the calculation in the PAS, we only have the one element. It rotates and forms all sorts of different L=2 objects, but we only need to predict this. Okay. Yes, please.
Sorry, I came in late, so maybe you already told them, but when we go back to relaxation theory, we're gonna need them all.
Oh, yeah, we said that.
Okay.
And we talked about a little bit about why. Okay, so this is like just calculating this one projection, and from that table, go back to the rules for an L=2 rotation. This is the only one, right? Our destination is n=0. Our source only had n=0. What is I? So we're going to take I naught, B naught from the spin degrees of freedom. We're going to take the delta and a geometric factor from the spatial degrees of freedom. And this is going to be our Euler angle projection factor, a bigger term, and it's I. What is I? Here's I. I happens to be 1/2 of 3 cosquare beta. We just pull that. So our Hamiltonian here, we restrict ourselves to lambda being CSA, L is only 2, M is only 0, and M prime is only 0 in this sum. So that's all we need for both sides. And D, we're not having an alpha and a gamma because we're uniaxial. So D is little d is 1/2 of 3 times beta minus 1. So actually there's no calculation. It's just a lookup. Sounds very computer program ready. You didn't look stuff up. You didn't calculate anything. You didn't multiply. Just filled in. But that was so easy because you took a minute to say, which do I need? Wait. Do I need L=0? No. Do I need L=2? No. Do I need L=2? Yes, but only. So that's the work is an intellectual job, just kind of choose the terms that you need and why. And if we have two frames, it does become a little more. But a single rotation and a truncated Hamiltonian is one line. So what we're going to be doing, and that's kind of what I just said, but I made a slide for it apparently. What we're going to be doing in the future has more than one frame. And so that's for Tuesdays. That's for Tuesdays to think about how to do that. I suggest you look at this problem that I just did very quickly for you. You say, I have a truncated Hamiltonian, and all it is place a crystal in a magnet and measure a frequency. So I need to convert from PAS to lab frame. Let me do it Cartesian slowly. See if you can find a mistake on my slide or something. And then I do spherical harmonic. And then I see if it's the same or are they like off. Does that make sense? As a way to review what we did this week and get ready for next. That one problem. And then there are two other problems you're going to be turning in, which are related. They're closely related to those two that we picked that week.
Which,
They're turning in for next week, 7 and 8 or something. 7 and 9.
Yeah, one of them is.
It's really just what I just laid you through. If you put away what I said, it probably just confuse you and do it by yourself and turn it into an issue. And the second one is system.
Well, the second one is the I4 plus CSA. Very nice.
Yeah, so you'll add the two.
Send an email to Anish
With your homework? Yes. Or you can copy me. You can also write for hints. You can write to either of us asking for a hint. Does that make sense? It's okay to ask one more question. I don't think we're getting kicked out of the room. Folks online? Complaints or questions? Good. All right, that's it for this week in that case.
You like me to continue with this conversation now?
Yeah, if folks can stay a little longer, if we have another 20 minutes. Yeah. That would be good, Anish. You're gonna get a lot of help for your homework, so it should be. Good.
I didn't see like an hour ago. Actually.
Who wants to?
Yeah, no, yeah.
If you-
So in the problem.
I guess if you join the,
Yeah. It is not a.
Zoom. Let me help you, let me do what,
Even the PowerPoint stuff.
I don't need the whiteboard.
so you're free to use this if this doesn't work, but I think all you need to do is put that in. Sign on to that Zoom. Right here. This version.
Yeah, but wondering if you have HDMI, so I can just go.
Oh, I have all sorts of cables.
Or maybe this.
I mean, the USB-C should work.
Yeah, I'm just saying I have an HDMI.
You're good, right? And you have to join this thing.
Which, yeah, I'm already there.
You're already in. So you're set.
Yes. My computer.
Use with, yeah, and then you form G.
Good. That's perfect.
That's what.
Okay. Yeah.
Hang on, my computer is just given up.
Oh, yes.
Maybe we could like
You should see.
use this around doing the board.
I don't know what is wrong with this. It needs like a computer to look at what I want to. Or talk about. No, it's the problem with my computer. Hang on. Little delay. Okay. Yeah, there is a bit of lag. I guess this is fine. If I can open what I need to open. Yeah. All right. So my screen is visible, and I think my computer is finally cooperating. This is not really a problem session, and we don't have a lot of time anyway. But I was thinking that to take a few steps back and revisit the fundamentals in a way that we can apply directly to the problem set and our understanding of solid state NMR broadly. So far in class, we have discussed the physical sort of picture or intuitive picture behind shielding as a phenomenon, where it is the effect of applied static magnetic field on the electron density, and that effect in turn manifesting as an induced electric field and the nucleus. And we broke that into three different parts. The first being an isotropic scalar component, that is the isotropic chemical shift. An asymmetric one rank component of the shielding, which does not contribute to the frequency. And the third being a second rank shielding tensor, which is what we refer to as the chemical shift anisotropy, which contributes to the frequency of a solid that is not, of a molecule or a system which is not experiencing tumbling. And tumbling here being isotropic rotation that averages this anisotropic frequency to zero on a time scale that is fast compared to that frequency. So in a system which does not have fast tumbling, this two-rank tensor results in what we see in solid state NMR as Fowler patterns. And in the class, we said that in the lab frame, for example, this symmetric CSA tensor can be written in this matrix form where 1, 1, 2, 2, and 3, 3 represent like the components, like as Anne had described. You apply a B field along axis 1, and then the induced field along axis 1 is sigma 1, 1, 2, 2, and sigma 3, 3. And then because we want a symmetric tensor, you take the averages of the off-diagonal components. And that's why you have 1, 2 plus 2, 1, half. And then 1, 3 plus 3, 1, half. 2, 3 plus 3, 2, half. And here I assume that the sum of these three components is 0, so that makes my matrix traceless. So now the question I'm going to ask is, this is representation of the matrix in an arbitrary axis system. Axes 1, 2, and 3, arbitrarily defined. And what is it that makes a given axis system the principal axis system for tensor? I wanted to go from this, and I wanted to represent the tensor in its principal axis system. What would it then look like?
Would the off-diagonal components be 0?
Right. So when I diagonalize a tensor, I get what is called the axis system in which the tensor becomes diagonalizable is the principal axis system. And in that principal axis system, you get zeros all over. And here I define x, y, and z as the principal components of the CSA tensor. I've of course chosen one out of the two conventions in NMR of naming the three different components. A quick note is that not all tensors are diagonalizable, or not all matrices are diagonalizable. And because we've imposed the condition of the tensor being symmetric and therefore Hermitian, we can diagonalize it and arrive at a principal axis system. But this is just saying sigma xx, sigma yy, sigma zz, and we commonly refer to tensor in terms of the width of the tensor being the anisotropy, and then an asymmetry or rhombicity. And we've looked at that representation and we've seen this. So if you're curious about how that works, this is the formula that you would use. And I'm just going to do a little exercise with these numbers, where delta tensor anisotropy is ZZ component minus isotropic, and eta is XX minus YY over delta. These definitions are important when you're trying to navigate the literature on some papers referring to the three components and some paper referring to the isotropic shift, the anisotropy, and the asymmetry. So if we wanted to go from XXYYZZ to the diagonal components in terms of delta and eta, what would we do? First, you notice that what is this quantity in the way I've defined it?
Sigma all three divided by, or the average of all.
Yeah, and I've set that to be 0, right? I've said that this average of the three elements is 0. So I'm just going to set that number to 0, which means that sigma ZZ is equal to delta, right? That makes sense? The ZZ component is equal to delta when the isotropic shift is set to 0. This is just like translation. And how do I get sigma XX and YY? In terms of delta and eta? You have one equation relating XX and YY. What is the other?
Sigma ZZ in place of delta.
So well, here
And
I'm saying we need to convert all three parts to a delta and eta.
oh,
So this is one relation connecting XX and Y. What's the other one? We said the average of the three is 0, right? So what does that give us?
XX equals minus sigma Y minus YZZ.
Right. So the XX plus the YY is negative of the ZZ component, which in turn is this. Right? Does this make sense? This is good with all of us. Not sure, I maybe got this wrong. And I'm going to ask you.
Yes.
Was the asymmetry defined as X minus Y or Y minus X?
X minus Y, I believe.
Minus Y. Okay, so I have this right. So then you just add up these two. Is this right? Not sure.
Y minus X.
Y minus X, yes.
Sorry.
So,
Um,
I don't know how I also got this wrong. So what I'm saying is you then add those two equations to get YY, subtract them to get XX. Does that make sense? Does this operation make sense? So you get XX is delta over 2, 1 plus eta, and YY is minus delta over 2, 1 minus eta. So now you can write the shielding tensor in the way that we have been seeing in the lecture. Right, so one of the problems the problem set is asking what frequency you expect. This is actually related to problem 1. What frequency you expect when the B naught is aligned along the x-axis of the principal axis system and then along the z-axis of the principal axis. What are the answers to those two questions? Right, so that's plus delta. 1 plus delta. Right. Now what happens to this tensor if beta equals 0? Or a rhombic sigma y. Right, so this is the tensor that I get. Minus delta over 2, minus delta over 2 delta. And this is what gives you something that Anne has showed you in lecture, which is a familiar fake pattern, where you get this turning point at minus delta over 2 and this turning point at delta. So delta being the point where V naught is aligned along the z-axis of the principal axis system. And that, as we were discussing, for a powder, there is limited space around it. And because this principal axis system is uniaxial, it doesn't matter where x and y. And because it doesn't matter where x and y are, all the positions on this equator are the same. So all the signal of the equator collects at minus delta over 2. You get this sort of pattern. Okay, so that was just a review of what tensors look like in frequency space, and so you can start to make sense of powder line shapes. I'm going to do a small little exercise where we just discussed how to rotate tensors using Cartesian method and then using the spherical tensor. I'm going to talk about how we could, arrive at the frequency of the Hamiltonian in the lab frame using the principal axis component of the CSA tensor using a Cartesian method. So one of the things that we discussed in class is this expression where we showed that basically you sandwich the shielding tensor between the static field and the spin angular momentum to account for the induced field. It's effectively what you're supposed to do is a dot product between the induced field and the spin angular momentum. But we've sort of taken that induced field in itself is represented by the shielding tensor. So you get this expression. V naught in the lab frame, sigma shielding tensor in the lab frame, I spin angular momentum in the lab frame. The important thing is that all three components, all three pieces of this puzzle, B naught, I, and shielding tensor, must all be in the same frame when you write this Hamiltonian. Does that make sense? So you can't have sigma in the PAS frame and the other two in the lab. And I know sigma in the PAS frame because that's easy, because it's diagonal. Right? And I just showed you how to calculate the diagonal component of the shielding tensor. If I know the diagonal component of the shielding tensor, then the easiest thing, one easy thing I could do is try and rotate these two vectors, which is V naught and the spin angular momentum, in the PAS frame. Does that make sense? Right, so I have done this rotation on the side. I've taken spin angular momentum IZ in the lab frame, and I've tried to apply a rotation matrix from the lab frame to the principal axis frame. And similarly, I've done that on the right for the static magnetic field. And of course, because it's a row vector, I have to apply an inverse rotation. Now you could, as was discussed in class, you could bunch together this R inverse and do this 3 by 3, 3 by 3 series of 3 by 3 multiplications that you can do. And you're doing unitary transform on the PS tensor to go into the lab tensor. But I'm going to use an approach that is outlined in the recommended reading, Schmidrow and HP's book, where they actually say, let's rotate the vectors. This is doing an active rotation of the vectors. Bring the vectors into the PAS frame and then calculate the frequency. And the reason that this is simple is because, of course, in the lab frame, B naught is just Z, right? There's only the Z component. This makes sense? It has no X and no Y. Static magnetic field is only on Z. And I make the simplifying approximation that the angular momentum is also only Z. And I ignore induced field along X and Y. This is truncation. I explicitly ignore the induced field and the required frequency term that arises from induced field along X and Y, because I believe that Z is so strong that the small induced field along X and Y is irrelevant. This is truncation. And now all I have to do is rotate these two vectors, and they are essentially identical vectors, right? B naught is along Z, and IZ is also along Z. So I just rotate both of these vectors in the principal axis. And so this is just my representation of how you can think about this. This is the Z-axis in the PAS frame. I'm just going to say ZP. This is the X-axis and this is the Y-axis in the PAS frame. Okay, so that's the principal axis system of the chemical shift tensor. And I'm representing B naught, or the Z of the lab frame, as this red vector. Does this make sense?
That's an arbitrary angle right now.
Yeah. So depending on how a molecule is oriented, right? So kind of like just going to draw carboxylate. This is the Z-axis, this is the X-axis, this is the Y-axis. And B naught is at some angle, depending on the orientation of the molecule in the magnetic field. And what we are trying to ask is, given this orientation, what will the NMR frequency be in terms of the CSA tensor component? This is the central question that we are trying to grapple with. Okay, now if I wanted to write this red vector in the PAS system as X, Y, and Z components, what would it look like? Just the red vector, that's the Z-axis of the lab frame, and I want to write its X, Y, and Z components in the PAS frame. First thing I can get is the Z component, right? Given these angles.
Cosine beta.
Cos beta, yes. So this is cos beta. That is cos beta. So then its projection onto the XY plane will be sin beta. Does that make sense? Projection along Z was cos beta, the projection into the XY plane will be sin beta. Then what is its X component? Sin beta was alpha. And what is its Y component? make sense? Then the Hamiltonian is very simply minus gamma b naught. Remember, I tried to write the b naught field as a row vector. So that becomes sine beta cos alpha, sine beta, sine alpha, cos beta, followed by the shielding tensor, the PAS. What are its components?
We're in the PAS, right?
Yep.
It's a good thing.
Yes. 1 plus eta. The next one is
minus. See that?
yes, we do.
Special. Something like that.
This makes sense. I'm just trying to cramp a lot of stuff into fairly short spaces where the terms will end up on back-to-back lines. So because the rotation of IZ and B naught is the same, so I just have a row vector on one side and a column vector on the other side. Does this make sense? Now, this is the great thing about having a diagonal CSA tensor, right? The matrix multiplication is very simple. So I'm just going to pull out this as one term, right? Then the second one, second, and then third. And the sum of all that, I have to put all that together, and out will come the NMR frequency. I'm just going to drop gamma b naught here because it's divide by h bar and get the frequency. So the first term is minus delta over 2, 1 plus eta, sine squared beta cos squared alpha. Right? So that is this, and then that. And I can do this. It's supposed to be a complicated multiplication, but because I have zeros of diagonal, comes out fairly straightforwardly. Then minus delta over 2, 1 minus eta, sine squared beta, sine squared alpha. Make sense? This is good with everybody? Okay. This expression looks kind of simple in the sense that I can take delta over 2 out, right? Common. I'm going to do that. So I get 1 plus eta sine squared beta cos squared alpha plus 1 minus eta sine squared beta sine squared alpha plus minus 2 cosine squared beta. Does this make sense? Any recommendations for simplification? After this is just trigonometry and more trigonometry.
Take our common sine square beta from the first and second term, the cos square alpha plus all these.
Yeah, there's eta hanging out in one side, but it's not hanging on the other side. Right? So I can do that. Which is equal to cos squared alpha plus sine squared alpha is equal to 1. Out there goes. Right? Can I simplify further?
You take minus out from the second term, you the cos square of minus sine square alpha,
Which is
cos 2 alpha.
right. That becomes minus eta sine squared beta cos 2 alpha. And what else? Sine squared beta and cos squared beta. Sine squared beta is 1 minus cos squared beta, right? So I get 1 minus 3 cos squared beta. Does this make sense? As you can see, quite a lot of algebra and trigonometry for one train transformation. And then you try and do this for nested frame transformation, going from PAS to molecule fixed frame to rotor fixed frame to lab frame. And you will start to see why this becomes untenable, at least by hand. And this really is why spherical tensors are valuable, so valuable for nested frame transformation. Because I applied a lot of simplification. I said, yeah, my tensor is diagonal, let me apply an active rotation on the vectors. And I still had to do a lot of trigonometry to arrive at the expression. But this is it. This is the expression for frequency of a crystalline having an orientation given by alpha and beta in a magnetic field with a tensor given by an anisotropy of delta and an asymmetry of eta. And of course, if you set eta equals 0, you get the familiar expression that we had today. Just this.
Now, when they derive these expressions for their homework, it'll be very similar to this, but you're not expected to necessarily take the same exact approach you take. Take an approach that is more strictly like right out of the lecture that I gave. So you rotate the tensor, not the spins.
And when, yeah.
And that would be a better exercise for you. If you simply recapitulate what Anisha has done for you, yeah, that's okay. That means you understood it, you followed it. But if you do it for yourself out of the tensors, that's another thing you can do.
Yeah, yeah. So there you rigorously apply
Right through.
and remember that you only need the 3-3 component. Because that's what you're going to pull out when you try and calculate the frequency and verify that you get the same expression that I got today. Okay, so hopefully this will help with the problem set. We are quite a bit over time. So any concluding questions? Okay, I hope this was helpful and see you next week.